Every year, 450 airplanes disappear forever, but they are not headed for a landfill, rather a hidden multi-billion-dollar dismantling industry, where every part has a price. A retired airliner rolls out of the baking desert sun and enters the dry, sterile air of a specialized processing hangar. Ground crews quickly lock the massive machine in place. The towing ends here. The aircraft is now a mechanical patient strapped to an operating table. But how do you safely kill a machine that still harbors lethal voltage? You cannot just grab a saw and start ripping through the fuselage. Engineers thoroughly inspect the airframe and draft a meticulous disassembly plan. Zero blind cuts. Before the heavy dismantling begins, the aircraft's entire nervous system must die. A technician ducks under the nose and pulls the avionics access panel. It drops open with a heavy metallic clank. He reaches into the dense thicket of wires. Fingers hit the primary breakers. Click. He violently disconnects the main power cables. He isolates every single backup battery source. The primary circulation stops, yet the real threat hides deeper. Aviation capacitors act like hidden venom glands. Even weeks after the engines shut down, these components tightly hold up to 800 volts of residual charge. That is enough raw electrical force to stop a human heart in 3 milliseconds. The technician firmly presses a grounding probe against the terminals. A sharp snap of static cracks through the confined bay as the deadly current bleeds harmlessly down into the earth. The last spark fades, instantly turning a highly complex flying network into a cold, dead metal carcass ready for the first surgical incision. Once the brain of the patient is completely shut down, aviation surgeons proceed to extract the most expensive organs, the engines. These power plants can cost tens of millions of dollars on the secondary market. Every ounce of attention in the hangar narrows down to a single massive structural bolt. A heavy-duty overhead crane takes on the dead weight of the turbine to prevent a catastrophic drop. The titanium bolt groans under the immense tension. Metal grinds against metal. A turbine weighing over 8,000 pounds, heavy enough to crush a commercial truck, hangs suspended in the air. Mechanics loosen the final threads with absolute precision. One slip means severe structural warping. The team safely lowers the massive engine onto a transport stand for future refurbishment. Next comes the foundation of the aircraft. The landing gear absorbs the brutal kinetic energy of touchdowns, making it the most robust physical structure on the airframe. Technicians position heavy hydraulic jacks underneath to stabilize the empty fuselage. Only then do they violently drive out the massive steel retaining pins. The sheer scale of this heavy extraction sharply contrasts with the cockpit teardown. While industrial cranes hoist thousands of pounds of forged struts, technicians delicately pull out navigation units, control modules, and flight computers. It is pure watchmaking. Fragile circuit boards against massive steel pylons. Precise, meticulous, highly profitable. These extracted systems hold the lion's share of the residual value of the aircraft, and the engines alone easily pay off the entire dismantling operation. But the machine is far from safe, as the most dangerous and volatile elements are still hiding deep inside the dead fuselage. But even without engines, the aircraft remains a powder keg. Trapped in its veins under enormous pressure are hundreds of liters of toxic hydraulics and aviation fuel. On the surface, the gutted metal shell sits completely motionless. Inside, it is a loaded weapon. The mechanical bloodletting begins with the deep, vibrating hum of industrial pumps. Thick hoses lock directly onto the fuel tanks hidden inside the wings and fuselage. They suck out the volatile kerosene with massive force. Flow control sensors monitor the closed loop continuously, tracking the transfer speed. One microscopic leak, one static spark, the entire structure detonates. With the wings completely dry, technicians hunt down the ultimate hidden threat, the hydraulic lines. Even entirely powered down, these narrow tubes trap up to 3,000 pounds of pressure per square inch. That is the weight of a full-size sedan crushing down on a space the size of a single coin. It is a dormant kinetic force easily capable of tearing solid aircraft-grade aluminum apart. Workers manually crack open the discharge valves in a strict, unforgiving sequence. A sharp, violent hiss erupts across the hangar as the trapped energy finally bleeds out into the open air. Heavy suction systems then strip the remaining toxic fluid from the pipelines. No residue, no trapped force, zero margins for error. A single pressurized drop meeting a metal cutter down the line would turn the fuselage into deadly shrapnel. The sharp hiss of the final discharge valve slowly fades into complete silence. The intricate circulatory system is absolutely empty, leaving the drained metallic carcass primed for the next, far more brutal stage. Drained of its blood and stripped of its engines, the aircraft is ready for one final humiliating procedure. It is being skinned alive. Technicians systematically rip out the soft tissues of the cabin. Polyurethane seat cushions, synthetic carpets, and molded polycarbonate panels are rapidly detached from the floor tracks. Over a fast-forwarded span of just 48 hours, the illusion of commercial flight completely dissolves. A cozy, climate-controlled space designed for 300 passengers devolves into a stark, ribbed industrial tunnel. Workers tear away the thick fiberglass insulation blankets. The sharp, ripping noise echoes heavily through the cavernous, emptying aluminum tube. Layer by layer, the yielding engineered plastics surrender to the cold rigidity of the primary load-bearing skeleton. The recycling industry demands this aggressive segregation for a strict chemical reason. Cabin plastics and composite foams burn at roughly 400 degrees Celsius, while aerospace-grade aluminum requires exactly 660 degrees to melt cleanly. If these unalike materials meet in the downstream shredder and hit the furnace together, the resulting toxic slag will fatally contaminate thousands of pounds of highly valuable metal alloy. The separation must be absolute. Every copper wire is pulled from the walls. Every overhead bin is unscrewed and hauled away. The sweeping fuselage stands entirely naked, stripped down to its green prime structural ribs. 0. That is exactly the number of non-metallic details remaining inside before the final stage begins. This empty metallic skeleton is just a fraction of a giant conveyor. What seems like the end for one machine feeds an entire industry. Every year, airlines permanently ground 450 commercial jetliners. They bypass traditional scrapyards entirely. Instead, they enter a tightly controlled multi-billion-dollar industrial pipeline. A modern airliner represents a pinnacle of human history and engineering. Up to 6 million individual components interact to defy gravity and transport hundreds of lives. Now, the system reverses that exact timeline. The ultimate aerodynamic structure devolves into a relentless stream of basic raw materials. Millions of parts, methodically cataloged, sorted, reborn. Recycling centers extract up to 90% of the aircraft's total weight, feeding the material directly back into global manufacturing. Aviation-grade aluminum, titanium alloys, copper wiring, clean, reusable, profitable. One gutted fuselage is merely a single cog in this massive mechanical network. The extraction line operates with cold, absolute logic, turning complex aviation history into heavy industrial commodity. But precision has its limits. As soon as the patient is stripped of everything valuable and the cabin is cleared, the most brutal phase begins. Excavators with heavy hydraulic jaws step in. The interior stands completely empty. Now, hydraulic shears begin to ruthlessly shred the structural frame, turning aviation pride into pieces of scrap. The heavy steel blades bite directly into the fuselage. Pressure builds. A deafening screech of tearing aerospace aluminum cuts through the industrial yard. The excavator jaws deliver over 1,000 tons of closing force, effortlessly slicing through the outer skin and internal support ribs. The ultimate mechanical test happens at the wing root. This is the structural core. During flight, these primary joints withstand dynamic upward forces equivalent to the weight of 3 diesel locomotives. The main spars here integrate dense titanium alloys, engineered to be as thick and rigid as a solid concrete pillar. The excavator operator positions the heavy blades right over this massive intersection. The steel teeth press aggressively into the spar. The metal deforms. The aerospace alloy bends. A violent crunch echoes across the tarmac as the wing root finally snaps in two. Ground crews quickly drag the severed wings, the heavy tail section, and large body segments into designated sorting blocks. The aircraft permanently loses its structural integrity. It is just raw material. The hydraulic jaws tear mercilessly into the remaining skeleton. Mutilated chunks of the fuselage break away from the main body and crash heavily onto the concrete pad. We jump straight forward to the melting shop floor. A giant industrial crane already grabs multi-ton batches of perfect, shredded scrap, ready to drop them into the electric arc furnace. Forget the slow logistics of truck deliveries. Here, sheer mass rules. The overhead industrial crane system takes absolute command. A massive grapple bucket it plummets from the ceiling. Steel teeth bite into 15 tons of jagged metal. That equals the weight of a fully loaded city bus, dangling from a single wire rope. The winch screams. The payload swings directly over the gaping mouth of the furnace. The jaws snap open. A deafening, resonating crash rips through the facility. Tons of shredded steel smash against the bare metal of the empty chamber. The violent impact shakes the concrete floor, yet engineers carefully control this brutal process. The system demands strictly dosed, layer-by-layer loading. The crane returns, grabs, drops, repeats. Every single payload dictates the upcoming thermal reaction. Overloading the vessel destroys the melting efficiency completely. An uneven pile creates dangerous cold zones inside the future liquid bath. Layer after layer, the metallic core builds up inside the belly of the machine. Then the crane retreats. The massive furnace roof swings shut, sealing the vessel. The roaring echoes fade away. A heavy, tense silence swallows the dark chamber, waiting for the fatal strike of extreme voltage. But hold on, how exactly did those giant wing fragments turn into these neat, perfectly sized chunks for the furnace? To get here, they had to pass through absolute hell, a system of massive industrial shredders. Before reaching the plant, the aircraft's carcass faces hydraulic excavators equipped with heavy-duty shears. These massive steel jaws do not just cut, they crush, fracture, and fold aviation-grade panels into transportable chunks. The real destruction happens next. A conveyor belt feeds the jagged wreckage directly into the shredding chamber. The process is brutal and continuous. A massive chunk of the fuselage drops onto the twin counter-rotating shafts. Hardened steel teeth immediately bite into the metal. They grip, they tear, they rip apart the aircraft's skin with terrifying efficiency. These massive rotors are driven by industrial motors packing over 4,000 horsepower, chewing through high-strength aerospace alloys as easily as if they were wet cardboard. The sensory impact is overwhelming. A deafening mechanical roar fills the facility, and a deep, relentless vibration pulses right through the solid concrete floor. In mere seconds, the machine spits out a stream of violently chewed, unrecognizable fractions from its discharge outlet. Now, a chaotic river of mixed debris flows down the sorting line. But how exactly does this machine distinguish aluminum from steel without a single human hand intervening? Physics takes complete control. First, a high-intensity overhead magnet hovers above the moving stream. It violently yanks out all the ferrous metals, pulling iron and heavy steel alloys upward and completely out of the mix. But a commercial airplane is mostly aluminum, and aluminum is not naturally magnetic. To catch it, the remaining material slides over an eddy current separator. Underneath the conveyor belt, a high-speed magnetic rotor spins at nearly 3,000 revolutions per minute. This rapidly changing magnetic field induces a temporary electrical current deep inside the aluminum fragments. The resulting magnetic reaction instantly repels the lightweight metal. The aluminum literally jumps off the belt, launching through the air in a perfect arc and landing in a separate collection bin. Advanced optical and induction sensors quickly identify the remaining stragglers, directing valuable copper wiring and solid titanium brackets into their own distinct streams, while non-metallic plastics are safely discarded. The chaotic mountain of shattered debris has been entirely tamed and classified. This chemically pure, perfectly sorted aerospace metal is now fully prepared for its ultimate temperature transformation. The crane jaws open. Tons of jagged aerospace scrap plummet into the heavy steel crucible. And now, this perfectly sorted mass collides head-on with 3,600 degrees Fahrenheit. The heavy furnace lid slides shut. 3 massive graphite electrodes slowly descend into the darkness. They stop just inches above the jagged metal mountain. Power surges through the cables. A blinding flash of artificial lightning strikes the scrap. The air around the steel shell instantly warps and trembles from the unbearable heat. We are looking at an electrical arc carrying tens of thousands of amps. Pure destructive energy. 3,600 degrees. That is roughly a third of the temperature on the surface of the sun contained inside a single industrial vessel. The physical structure of the metal stands no chance against this environment. The solid steel turns violently red. The sharp edges soften. The rigid alloys simply give up and flow. The aircraft completely loses all memory of its former aerodynamic shape, collapsing into a glowing primordial soup. The acoustic shockwave of the arc is absolutely deafening. It sounds like a continuous jet engine takeoff trapped inside a steel drum. Additional scrap is relentlessly charged into the inferno to maintain the critical volume of the melt. But melting is merely the brute force phase. Next comes the chemical purge. Lime and engineered fluxing agents are blasted directly into the liquid pool. They hunt down non-metallic impurities. These agents aggressively bind with unwanted elements, dragging them away from the valuable steel base. This toxic chemical cocktail rapidly rises to the surface. It forms a thick, glowing crust of slag. Heavy automated rakes physically scrape this contaminated foam away from the pristine liquid beneath. Deep inside the vessel, thermal sensors and probes quietly monitor this chaotic environment, confirming the exact molecular recipe without interrupting the violent flow. Zero structural memory. Absolute chemical purity. The chaotic debris is gone, and a completely purified, red-hot mass of homogeneous metal violently surges toward the exit, ready to burst from the furnace. But molten steel does not stay in the furnace for a single second. It pours out as a boiling river to immediately take on a new form. A guided tapping system channels the relentless flow directly into water-cooled casting molds. Here, a physical paradox unfolds. As the incandescent metal hits the chilled walls, the outer layer freezes instantly. A rigid shell forms. Inside, the core remains pure churning liquid. This fragile structure cannot stop. The material continuously moves forward over a series of heavy rollers, radiating immense heat while slowly cooling from the outside in. The continuous stream stretches into an endless glowing ribbon extending for dozens of feet, effectively forging the new building blocks of the world. Whether destined for heavy construction or flat sheet rolling, the continuous process demands a clean finish. An automated cutting system aggressively intercepts the moving line, slicing through the steel river to divide the flow into standardized sections. Hundreds of new, perfect steel billets head down the conveyor. Burning billets fly from the casting floor straight into the ruthless jaws of the hot rolling mill. The air trembles and blurs from the sheer fiery heat, carrying the dull, heavy hum of compressed steel. An incandescent block slams into the continuously rotating rollers. The gap violently shrinks. With a deafening crunch, the dense steel is forcibly squeezed and stretched into a long, luminous ribbon. At roughly 1,200 degrees Celsius, the metal remains entirely ductile. The machinery aggressively kneads the glowing mass, physically tearing and realigning its internal grain structure while it is still vulnerable. The physics at play are brutal. The pressure exerted by these massive steel cylinders is staggering, equivalent to the entire dead weight of 3 freight locomotives pressing down on a single isolated point. The material drives through multiple successive stages, and the operation never stops. With every single pass, the opening between the rolls grows tighter. The steel is forced to become exponentially thinner and longer, leaving absolutely no room for structural weakness or cracking. Precision is violently enforced. Laser sensors constantly monitor the thickness and speed of the rushing material in real time, reading the metal's profile in milliseconds. At the absolute slightest deviation, automated systems instantly adjust the roller gap, zero margin for error. Because the material stretches continuously, its velocity must dramatically increase to prevent a catastrophic bottleneck. By the time the steel reaches the final stands, the elongated ribbon whips through the machinery at speeds exceeding 80 kilometers per hour. The continuous chain of extreme heat and colossal pressure smoothly transforms thick, raw slabs into flawlessly uniform sheets and densely wound products. Glowing red coils glide further down the conveyor into the unknown. But for a glowing coil to become a fully functional part, it must survive a zone of extreme thermal stress and paranoid control. The red-hot metal flies straight into a curtain of high-pressure water mist. Aggressive hissing fills the chamber. Steam explodes from the steel. The temperature plummets by hundreds of degrees in mere seconds, a thermal plunge violent enough to shatter ordinary glass. Instantaneous surface darkening follows. A cold, metallic gleam emerges on the outside, but inside, the threat remains. The freezing exterior of the hardened shell clashes violently with the still glowing, unstabilized core trapped within. This is the thermal shock threshold. If the internal heat escapes too rapidly, the molecular lattice simply tears itself apart, cracking the steel from the inside out. Brief ambient air circulation prevents this, gradually bleeding out the deep internal tension until the core completely settles. Once stabilized, the uncompromising inspection begins. An invisible spectrometer beam hits a fresh cut on the metal. It it instantly vaporizes a microscopic layer to read the exact chemical fingerprint of the batch. Carbon, manganese, and silicon levels flash on the monitors. Simultaneously, hydraulic presses stretch and crush test samples to verify ultimate tensile strength and hardness. The margin for error is zero. The slightest chemical deviation, or a fraction of a second miscalculated in the cooling speed, sends an entire 50-ton batch straight to the scrap heap. The surviving metal moves down the line, where industrial shears aggressively sever the material into standardized segments with a cutting precision of exactly 1 millimeter. These perfectly sliced pieces of steel from the spectrometer are not just nameless material. They are the absolute reincarnation of a machine that has already flown thousands of hours. Every heavy ingot carries a hidden history of decades spent in the freezing stratosphere. Millions of miles and countless atmospheric pressure cycles are now compressed into a single standardized block of raw potential. A decommissioned airliner does not simply rot in a dusty boneyard. Heavy machinery brutally tears the hull apart, shreds the fuselage into unrecognizable fragments, and prepares the core for total reconstruction. Inside the roaring furnace, extreme heat aggressively cleans and purifies the metal, incinerating every trace of its former life. By reclaiming this highly engineered alloy, the facility bypasses the massive environmental toll of mining, saving 95% of the energy required to produce virgin material. The intense melting process forces a complete molecular reset. The recovered metal emerges with physical properties and tensile strength absolutely identical to freshly forged parts. Zero flaws, pure quality. The life cycle of this industrial titanium and steel refuses to end with one single retired jet. Where will this fragment of the sky, having just survived the extreme violence of the melting furnace, end up tomorrow? The purified metal is fully ready to become the vital skeleton of a completely new machine, but to make that physical leap, it urgently needs a digital passport. The pneumatic press strikes with a sharp mechanical crack, stamping a rigid tracking code directly into the cold metal surface. To make this reincarnation physically happen, each batch receives a unique digital passport and instantly integrates into the global bloodstream of heavy logistics. There is no time for routine warehousing on wooden pallets. Massive transport shipping containers swallow the dense metal blocks with a resonant, dull thud, securing the cargo for immediate planetary dispatch. Absolute traceability dictates the final route. One single batch of this forged metal scatters to dozens of different manufacturing plants across the globe. The scale of distribution is massive. These purified blocks feed the relentless stamping presses of the automotive industry and form the hidden structural anchors inside towering commercial skyscrapers. But a highly specific fraction of this alloy demands a strict return to its origins. It flows directly back into the aerospace sector. The torn, weathered skin of a dismantled jet smoothly transforms into the flawless structural ribs of a completely new machine. Right now, 30,000 feet above our heads, a passenger jet cruises through the freezing stratosphere, literally assembled from the metal bones of past aviation. The cycle is complete.